All right, now let's take a look at our third sample problem. So once again, I'm going to read the problem. If you haven't tried it, I recommend you try it, pause the video, and then watch the solution. So Zion wants to become a millionaire by the time he's 40 years old. Pretty ambitious, right? He's worked very hard in life, and at age 30, he currently already has $500,000 or $500,000. If he puts this amount into a savings account that earns a 1.8% interest compounded monthly, how long will it take him to reach his goal of being a millionaire? Will it be by age 40? All right, so pause the video, give it a try if you haven't. I'm gonna go ahead and show the solution. So remember, we always start with our formula, B equals P times 1 plus R over N to the power of NT. And then we're going to identify the information we know. So we know that the balance he hopes to achieve is a millionaire. So we know that's our B. I shouldn't have chosen that color. Let's use a better color. So millionaire, that's our balance. All right. Now, we also know that he currently has, or our principal he's depositing is 500,000. So that's our P. We know that he is putting it into an account that has a rate of 1.8. Just keep in mind, when we plug this into the formula, it will go in its decimal form, 0.018. And we know that this account is compounding monthly. So that's 12 times in the year. So N will be 12. That's our frequency. Now, the only piece of information we do not know is how long. So that's our variable T. And that's what we'll be solving for here. So we're going to start by plugging in everything we know. So we're going to do 1 million is equal to 500,000 times 1 plus a 0.018 over 12 to the power of 12t. Now, just like before, I think the best first step is going to be simplifying that part inside the parentheses, that 1 plus 0.018 over 12. And we could see that that's a 1.0015. 1.0015. Everything else will stay the same. So I'm just going to rewrite it. So 1 million is equal to 500,000 times our 1.0015 to the power of 12t. Now from here, remember, we are going to reverse PEMDAS. We're going to undo this. So is there any addition or subtraction? No. Is there any multiplication or division? Yes. We can see that 500,000 is being multiplied here, and we want to remove it away from the same side of the equation as the t. So we're going to divide both sides of the equation by 500,000. Okay, 500,000 divided by 500,000 is 1, so those cancel. And on the left-hand side, we have 1 million divided by 500,000, which is 2. So we have 2 is equal to 1.0015 to the power of 12t. Now, at this point, we want to remove our variable power. So in order to do that, we're going to take our common logarithm of both sides. Log of 2, and then our log of 1.0015 to the power of 12t. Now, the awesome thing is here, we're going to use our power property, which will then remove the power. So now we have log of 2 is equal to 12t times the log of 1.0015. Now remember, our objective is to get that variable by itself, so we're going to go ahead and divide by anything that's with that t. So we're going to divide by 12 times log of 1.0015, and we're going to do that on both sides to keep our equation balanced. On the right-hand side, the 12s and the log of 1.0015 cancel, and now we're going to use our calculator to figure out our value. So we have our log of 2 divided by, in parentheses, 12 times our 1.0015, our log of that. We'll look up here and make sure it looks how we intend, right? We've grouped the denominator, and then we hit enter, and we could see that the time is about 38.54 years. So let's just say 38.5 years. Now, obviously, that will be a slight underestimate, but I'm okay with that. We can go up if we need to. So 38.5. All right, let's go ahead and verify that using Desmos. So this was 500,000, 1.8 monthly. So 500,000, and that was a 1.8 monthly. And we were hoping that it would be 38.5 years to get that million, 38.5. And we could see here we're just shy of a million. Let's try 38.6 is too high, right? That's why it was that 38.54. Okay, but 38.5 is really close. So obviously you could argue it would have to be more than 38.5, right? So maybe a 38.6 would get you there, right? But 38.5 is very close.